Good day, this video is about Introduction to Survival Analysis. Survival analysis, or also called as the time to event analysis, is the branch of statistics used to analyzing the expected duration of time until one event occurs. And this event may be the time until the first pregnancy occurs, the time until getting cured to a specific disease, or the time until death occurs. Now, suppose we have a data of 10 patients, and then this is the start of their therapy, and then this is the last observation, and then the duration. For example, March 1 to April 1 is 1 month, May 1 to June 15 is 1.5 months, April 1 to May 15 is 1.5 months, and so on. And this is the event wherein 0 means right-censored. And when we say right-censored, the event of interest has not occurred yet. So meaning, after 1 month of observation, this patient hasn't died yet. On the other hand, the second patient here, which was observed after 1.5 months, and it was observed that the patient already died during this point in time. The third patient, which was observed from April 1 to May 15, in that is 1.5 months, died. The fourth patient, June 1 to August 1, meaning after 2 months, the patient hasn't died yet. July 1 to September 15, so that is 2.5 months, the patient died. August 1 to November 1, meaning after 3 months, the patient died. August 1 to November 15, after 3.5 months of observation, the patient hasn't died yet. August 15 to December 15, so that is 4 months, the patient hasn't died yet. January 1 to May 15, that is 4.5 months, patient already died. And February 1 to July 1, so that is 5 months, which is the last observation, meaning the patient hasn't died yet. Okay, so 1 here means the event already occurred, or in other words, the patient died, while 0 means the event has not occurred yet. Now, we may display this data into what we call as the Kaplan-Meier curve, which is a graphical representation of the survival curve across the observation period. A vertical drop indicates the event or death has occurred. Starting at the first patient who was observed after 1 month, the patient hasn't died yet. So meaning after 1 month, no patient has died yet. So in other words, they are still complete after 1 month. So I'm going to put it here. So 100% of them are still alive. However, after 1.5 months, 2 patients already died. So this is 1.5 months. 2 patients already died at that point, so that makes it 80% of survival. Okay, so that's 80%. Next, after 2 months, no patient died. So I'm going to put a horizontal line. 2.5 months, 1 patient died. So at 2.5 months, that's somewhere here, 1 patient died. So meaning that makes it 70% probability of survival, meaning 7 out of 10 of them are alive after 2.5 months. But after 3 months, another patient died. So I'm going to put here, after 3 months, another patient died. So that will be another vertical drop. 3.5 and 4 months, no patient died. So 3.5 and 4 months, no patient died. But after 4.5 months, another patient died. So this is 4.5 months. There will be a vertical drop there. Okay, so that is 0.5 because 5 of them are already died, or 5 of them are still alive during that time. And in this case, after 5 months, okay, no patient died. So this is what we call as the Kaplan-Meier curve. We may illustrate it using this one. And we notice here that there are some special points here. These are 1 month, 2 months, 3.5, and 4 and 5 months, okay, which are the dates in which this are observed, meaning these are censored data. Okay, we're in a vertical drop which occurred after 1.5 months, 2.5 months, 3 months, and this one, which is 4.5 months, are the dates wherein a patient or patients died. And of course, the Kaplan-Meier curve is not limited to a single group of patients. As we can see here, we have two groups of patients which are under control, meaning they're not given the treatment, and one group which is given a treatment. So here we see a data on ID numbers 1 to 12, which are the control group, meaning no treatment was given. A separate Kaplan-Meier curve was constructed, and another group of patients from ID 13 to 24, which were given treatment. So another Kaplan-Meier curve was done here. And the control here is the one represented by the red curve, and the treatment group is the one represented by the blue curve here. And if asked, for example, it seems that patients who receive the treatment have less survival. It is because the blue curve here is under the red curve. So a curve that is below the other one means less survival. Okay, now suppose that a co-doctor asks, are you sure? So we have to perform a statistical test to answer that question. And that statistical test is what we call as the log rank test. Now, the log rank test has the null hypothesis that the probability of death at any time point of those who took the treatment and those who did not, which is the control group, do not differ. And the alternative hypothesis is that the probability of death at any time point of those who took the treatment and those who did not differ. So in other words, on the null hypothesis, the survival is just the same, while the alternative hypothesis indicates that the survival differ. Now, to perform the log rank test, we have a test statistic, which is basically a chi-square, which is written in this form. Okay, wherein the degrees of freedom is the number of groups minus 1. Now, to calculate the chi-square test here, we have to list down first all the time, in this case, the months in which the event or death occurred. So meaning 1.5, 2.5, 3, and 4.5 has to be listed down. So that's 1.5 because death occurred after 1.5 months, 2.5, 3, and 4.5. Okay? For the treatment group, it's 1. So we have to add 1 here, 1.5 as well, 2, 2.5, 3. So we have to add here 2 because after 2 months, death occurred in the treatment group. 2.5, 3, what else? 4, 4.5, and 5. So we have to add 4 because after 4 months, death occurred again in the treatment group. 4.5 on both groups and 5. Okay, so that's 1, 1.5, 2, 2.5, 3, 4, 4.5, and 5, which is the one written here. Okay, so these are the time, again, in months in which death occurs in either or both groups. Now, we have to list down in the control and the treatment group the observed outcome. O means death occurred while Q means censored. Okay? So, after 1 month in the control group, this is censored, meaning the event did not occur. That's why this is 1 out of the 12 patients in the control group. So, this one was observed, so leaving with 11 patients left, in which next is after 1.5 months, 2 patients died in the control group. That's why this is 2, and no patient is right censored or censored. Next, on the second month, this is 0. So on the second month, the event did not occur. That's why this is 1. After 2.5 and 3 months, 1 patient died on both. So this is 1 and 1 on 2.5 and 3. Next, 3.5 months, the event did not occur. However, 3.5 is not listed here. because after 3.5 months, okay, no patient died. That's why it's not written here. However, we're going to put this on the one that is earlier. Okay, so 3.5 months, the time earlier than that is 3. Okay, that's why there's also one here because of this one. Okay, so this was listed as 3, not as 3.5. It's because 3.5 again is not listed here. So we're going to place this patient who did not die on 3.5 months on the 3-month period, okay, or on the 3rd month. So meaning if the patient hasn't died after 3.5 months, we are sure that he also hasn't died yet after 3 months. Next is after 4 months, no patient died. So after 4 months, the patient did not die. 4.5, there's one who died and one did not. So that's why 4.5 here is 1 and 1. And after 5 months, no patient died. So this is 2 under the Q column. Okay? So what you notice here is that the number of patients decreases as well on the N column. So 12 and then 1 was already observed. So that's 11. On those 11 patients, 2 patients was observed and they both died, which are here. So that leaves with 9 patients left. And then among that 9 patients, after 2 months, 1 did not die. So that leaves with 8 patients. So 8 and then minus 1, we have 7. Then 7 minus 2 here, we have 5. And then 5 minus 1 here, we have 4. And 4 minus 2 here, we have 2. Okay? Or in other words, we may do it backwards. So this is 2. So this is 2. 2 plus 2 here, that is 4. 4 plus 1, that's 5. 5 plus 2, that's 7. 7 plus 1, that's 8. 8 plus 1 is 9. 9 plus 2 is 11. And 11 plus 1 is 12. So that's one way to check whether we were able to capture all the patients under this column in which event occurred and this column which is the censored data or the right censored observations. Okay, now on the treatment group, so 1 patient died after 1 month. So this is 1 and this is 1 among the 12 patients. Okay, so 1 patient was already observed living with 11 patients. So after 1.5 months, 2 patients have died. So meaning 2 patients died after 1.5 months. So that's 2. So 11 patients, among those 2 died or 2 was observed already. So living with 9 patients. On the 2nd month, 1 patient died. So that is 1. So 9 minus 1, we have 8 patients left. And then 2.5 months, another patient died. So 1 here. And then after 3 months, 1 died, 1 did not. So this is 1 and 1. So among the 7 patients, so these are the 7 patients. On the 4th month, 2 patients did not die, but 1 patient died. So after 4 months, so 1 patient died and 2 did not out of the 5 patients. And then we're left with the last 2 patients in which both died after 4.5 and 5 months. So that's why this is 1 and 1 after 4.5 and 5. Okay, after doing this, we have to add another column, which is the expected counts, which is E for the control and E for the treatment group. Now, E is calculated. Now, this is for the control and this is for the treatment group. So that is N sub 1 over N sub 1 plus N sub 2 times O sub 1 plus O sub 2 of or the number of patients who died. Okay, so O here are the number of patients died. And here is the total number of patients. Okay, so let's apply this equation. So this 0.5 is calculated as N sub 1. So that is 12 over N sub 1 plus N sub 2. So this is your N sub 1 and N sub 2. So N sub 1 plus N sub 2, we have 12 plus 12 times O sub 1 plus O sub 2. So that's 0 plus 1. So that's 12 times 1 divided by 24. That's why this is 0.5. Now let's try this too. How was this computed? So n sub 1, we have 11. So this is your n sub 1 and this is your n sub 2. So 11 over 11 plus 11 times O sub 1 plus O sub 2. So this is O sub 1 and this is O sub 2. So that's 2 plus 2. Okay, so that's 11 times 4. That's 44 divided by 12. We have 2. Let's try another one. How was this 1.33 computed? So applying this same formula, we have here, this is your n sub 1, this is your n sub 2, this is your O sub 1, and this is your O sub 2. So that will be n sub 1. So that's 4 over 4 plus 2 times O sub 1 plus O sub 2. So that's 1 plus 1. So that's 4 times 2. So that's 8 divided by 6. So that is 1.33. Okay, so same thing was done in the other values. Now for the E sub 2, all you have to do is to replace n sub 1 with n sub 2. These are the same as the one in the formula above. So for example, how was this 0.67 calculated? So that's n sub 2 over n sub 1 plus n sub 2, O sub 1 plus O sub 2. So in other words, this is your n sub 2, this is your n sub 1, this is your O sub 1, and this is your O sub 2. So that is 2 over 4 plus 2 times O sub 1, which is 1, plus another O sub 2, which is 1. So that's 2 divided by 6 times 2. That is 4 over 6 or 0.67. So I hope this calculation of E sub 1 and E sub 2 are clear using this. So in other words, this is just your n sub 1 and this is just your n sub 2. And this is O sub 1 and this is O sub 2 in each row. Okay? Now, to calculate the next column, we have O sub 1 minus E sub 1. So this is O sub 1 minus E sub 1. So that's 0 minus 0.5. So that's negative 0.5. 2 minus 2 is 0. 0 minus 0.5 is negative 0.5 and so on. Then you just have to add. So that's negative 2.5. So similarly, on the other side, so that's O sub 2, which is this one, minus E sub 2, which is this one. So 1 minus 0.5, we have 0.5. 2 minus 2, we have 0. 1 minus 0.5, we have 0.5, and so on. And then you just have to add, we're also going to have 2.5. Now, you just have to choose later which one are going to use, the negative 2.5 or the 2.5. Actually, it doesn't matter. Now, for the denominator, which is the variance, you have to calculate using this equation. So the sum here indicates you're going to add all of this. So each value is composed of this one. And that's the one written here. So let's start with this one. How was this computed? So this is n sub 1, 12, times n sub 2, which is 12. So that's 12 times 12 times O sub 1 plus O sub 2. O sub 1 plus O sub 2. So that's 0 plus 1. Multiplied to n sub 1 plus n sub 2. So that's 12 plus 12. We have 24 minus O sub 1 plus O sub 2. So that's 1. Divided by n sub 1 plus n sub 2. So that's 12 plus 12. So that's 12 plus 12 squared times n sub 1 plus n sub 2, which are again 12 and 12 minus 1. And calculating this value, we have 0.250. How was this computed? 0.467. So that's n sub 1, 8. N sub 2 is 8. O sub 1 is 1. O sub 2 is 1. So that will be 8 times 8 times O sub 1 plus O sub 2. So that's 1 plus 1. So that's 2. Multiplied to n plus 1 plus n sub 2. So that's 16. Minus O sub 1 plus O sub 2. We have 2. All over n sub 1 plus n sub 2 again. So that's 8 plus 8 squared times 8 plus 8 minus 1. So you just have to do it across all the rows here and get the sum. That will be the variance of O minus E, which is the one here. Now, further, since we had a while ago, we had 2.5 and one is positive, one is negative, and I told you that it doesn't matter because on the next one, O minus E here, which is 2.5 or negative 2.5 will just be squared. And then the variance, which is 3.113, will be the denominator. And calculating that, we have 2.008 as the value of the chi-square test statistic. Now, for the DF, since we have two groups, so that's 2 minus 1, leaving us with 1 degrees of freedom. And of course, we're going to compare it with the critical value in which chi-square test with degrees of freedom of 1 at 5% level of significance as 3.841. And since the test statistic is not beyond the critical value or does not exceed the critical value, then our decision is we're not going to reject the null hypothesis and conclude that there's no sufficient evidence that the probability of death at any time point of those who took the treatment and those who did not differ. And of course, the critical value is calculated in R using Q chi-square parenthesis 0.95 and 1. And we may get the p-value as well as 1 minus p chi-square and then the test statistic, which is 2.008, comma, and then the degrees of freedom, which is 1. And that p-value is 0.157. And since that is greater than the level of significance, which is 0.05, then still we're not going to reject the null hypothesis. Now, that is the manual calculations involving the log-rank test. Of course, we may perform that in R. So we may open the file toTreats.r data, and then before performing the log-rank test, make sure that you installed already the package which is called a survival. So to do that, we have to type install.packages, then in parentheses and close quotation marks survival. Then after installing that, we have to type library and then parentheses survival. And then after that, to run the log-rank test, we have to type serve diff, or in other words, the survival difference. Then in parentheses, serve, which is in capital S. And then in parentheses, the two variables of interest, okay, which is the time in which in toTreats.r data, that is time with capital T, comma, and then other column, which is the outcome, which is death in capital D, and then tilde, and then the group, we have the treatment group and control group, which is under the group column, so that's group, comma, and then again the data file, which is toTreats. And then we're going to see this result, in which as we can see that the chi-square test statistic is 2.0 with degrees of freedom of 1, and the p-value of 0.2, which is rounded off. So we know that that should be 0.157. And then we see here that in the control group, 5 died, okay, which is the observed deaths. And then in the treatment group, 9. Okay, so these are the events or the number of patients died. So 5 out of 12 died and 9 out of 12 died on the two groups. Now, further, we may construct the Kaplan-Meier curves using what we call the serve-fit function. So all we have to do is to type serve-fit and then the same functions in the parentheses. We have serve in capital S, time, comma, death, and then tilde, then group, comma, and then toTreats. And we see in the result that still 5 patients died in the control and 9 patients in the treatment. And what's special here is that it has the median survival time, which are 4.5 and 3.5. Now, where did that come from? As we see on the Kaplan-Meier curve, this is 0.5, and that happens between 3 and 4 months in the treatment group, the one that is in blue. That's why the median survival time for the treatment group is 3.5. Now, for the control group, as we can see, the median, which is again 0.5 survival, happened here, which is on the 4.5 months. Okay, that's why the median of the control group is 4.5 months. But again, there's no sufficient evidence that the survival of the two groups differ. So in other words, this median survival time do not differ as well. So there's no sufficient evidence, again, that the probability of death at any point in time of those who took the treatment and those who did not differ. Now for us to construct the Kaplan-Meier curve, all we have to do is to type plot and then in parentheses serve fit. And then the same functions in the parentheses we have serve in capital S, parentheses time, comma, death, and then tilde group, and then comma, and then two treats. Now what happens there is that it will graph the Kaplan-Meier curve, but without color yet, without the labels, etc. So for customization, we have to follow it up by some options like the LTY equals C parenthesis solid and dashed, so that the first group, which is the control, will be in solid lines, whereas the second group, which is the treatment, will be in dashed. And then col equals C for red and blue, so that will make the first group, which is control, as red and blue as the second group. And then the labels like X lab equals survival time in months and Y lab equals survival probabilities. So that will give you a Kaplan-Meier curve with colors and labels. However, it does not have the legend yet, which is placed on the upper right corner. So we have to put it legend, parenthesis, and then if you want to put it on the top right corner, please top right in close quotation marks, and then C parentheses, and then in close quotation marks, control and treatment for the first and second groups. And then the same type, which are in LTY equals C solid and dashed, and then the colors, which are red and blue. So it will match the two curves that we have just graphed. Okay, so that is for the plot and the legend. So again, using this data, we can see that the survival rates are 58.3, which is since out of 12, 5 patients died. So meaning 7 patients survived in the control group. And for the treatment group, since 9 died out of 12, so this is 3 out of 12 or 25% for the control group for their survival rates. And the median are 4.5 again and 3.5. But then again, note that this do not differ since the p-value in the log rank test is greater than 0.05. Now, do not be limited with the log rank test being applied to only 2 groups, because the log rank test may also be applied even you have 3 or more groups. Just like in the COVID data.r data that we're going to have, in which this is about a medical doctor who is interested in comparing the survival rates of admitted COVID-19 patients who were classified as moderate, severe, and critical. So here we see 3 groups of patients which are again moderate, severe, and critical. So data are stored in COVID data.r data, and the question is, are the probability of death at any time point of moderate, severe, and critical COVID-19 patients differ? Test at 5% level of significance. So of course, the first thing that we have to do is to construct the null and the alternative hypothesis, in which the null hypothesis is that the probability of death at any time point of moderate, severe, and critical COVID-19 patients do not differ. And the alternative hypothesis is that the probability of death at any time point of moderate, severe, and critical COVID-19 patients differ. And opening the data, COVID data.r data, we see 3 essential columns, which are the hospital stay, which is the time, the COVID class, which is 3 classes here. We have severe, critical, and moderate. And the outcome, in which 0 means censored and 1 means the death already occurred. So here we can construct the Kaplan-Meier curve by typing plot, parenthesis, serve fit, parenthesis, capital S, and serve, and in parenthesis, the time, which is hospital stay, comma, and then outcome. and then tilde the groups again, which is the COVID class in this case, comma, and then COVID data. And then we may also put the options there like the color, which are red, blue, and green, X lab, which is the hospital stay in days, and the Y lab, which is the survival probabilities. Then while it is being displayed, we may type in legend, and then if you'd like to put the legend on the upper right corner, we have to put in quotation marks top right, and then C, and then the levels in the COVID class, which are moderate, severe, and critical. And then likewise, we may put LTY equals C parenthesis solid in quotation marks and color, which are red, blue, and green. So here we see the Kaplan-Meier curve. And it seems here that there is a less probability of survival among the critical COVID-19 patients, because that is the one under the two groups, which are severe and moderate. And further, we may calculate the survival rates using the SURVIT function. So the SURVIT and then parenthesis serve hospital stay, comma, outcome, and then tilde COVID class, which are again the time, the outcome, and the groups involved, and then COVID data. And then the output will be again the events, or in other words, the number of patients died. So here we see 5 patients out of 89. So thus the survival of those who are moderate will be 84 out of 89. So that is 94.44%. For the severe patients, we have 23 patients who died out of 191. So the survival is whatever is 191 minus 23. So that's the number of patients who survive over 191. So that is 88%. And for the critical patients, we have 125 patients who died out of 241. So the survival of critical COVID-19 patients here, we have 241 minus the 125 who died over 241. So that is 48.1%. So here we see that it seems really that those who are critical COVID-19 patients have less survival as compared to the other two, but we don't know. And then the median time here, since this is NA, in other words, if we're going to put 0.5 here, we can see that the severe and moderate patients did not reach that point. That's why that is not applicable. However, for critical patients, it reached the 0.5 survival probability. So this is the intersection here. So that's around somewhere here, between 10 to 20. And that is calculated by R, and that is 15 days. So the median survival time of critical COVID-19 patients is 15 days. Meaning on the 15th day in the hospital, patient has 50-50 chance either to survive or not. So that is what do we mean by the median survival time of 15 days. Now, next we have the SURVDIF function. We have SURVDIF parenthesis serve hospital stay, comma, outcome, and then still on after tilde we have the COVID class. And we see that the chi-square test 74.6 with degrees of freedom to 2. Since we have 3 groups here, minus 1, so that's 2 degrees of freedom. And the p-value is less than 0.001. Okay, so since that is less than 0.05, then we're going to reject the null hypothesis and conclude that there is sufficient evidence this time that the probability of death at any time point of moderate, severe, and critical COVID-19 patients differ. So the survival or the probability of death at any time point of those 3 groups differ. So it seems that based on this graph, the probability of survival of the critical COVID-19 patients is less as compared to these two. But we're not sure yet. Now, to quantify how much one group is more at risk to die, okay, or more at risk that the event will occur on one group versus the other, because as we can see, the log rank test will not tell whether one group is more at risk than the other. It will not tell which group is that. So The next part is we're going to measure what we call as the hazard ratio. Now, the hazard ratio is a measure how often a particular event, in this case, death, for example, happens in one group compared to others, okay, over time. So in cancer research, hazard ratios are often used in clinical trials to measure survival at any point in time in a given group of patients who have been given a specific treatment compared to a control group given another treatment or a placebo. This was actually introduced by Mr. Cox or David R. Cox. He is a statistician who is also responsible for the logistic regression. Okay, so we have already discussed in the previous video the binary logistic regression. So he's also the one responsible for that. And this regression model that measures the hazard ratio is called as the Cox regression model, or also known as the proportional hazard regression model. So for us to perform the Cox proportional hazard regression model, or also known as the Cox regression model, all we have to do is to type Cox PH and then in parentheses the same function served with capital S, in parentheses hospital stay, comma, outcome, then tilde, and then COVID class. And then the data, we have the COVID data. So on the output, we will see some coefficients, which is the betas, and similar with the logistic regression, wherein the odds ratio is computed as the exponential of the betas. Similarly, in the hazard ratio, that is calculated as the exponential of the beta. So that's why we see some exponential and coefficient here. However, this does not include any confidence interval. So if we want to put a confidence interval, we have to put the word summary right before that function. Okay, so that's summary, parenthesis, and then exactly the same function. Cox PH, parenthesis, serve, parenthesis, hospital stay, comma, outcome, tilde, COVID class, comma, COVID data. So what we see here is actually the same result as the Cox PH result, but additional result were given in the summary function, which is the 95% confidence interval, which is displayed here. So let's start with the result generated by the Cox PH. Now, the coefficients here are actually your betas. Let's say the COVID class severe is your beta 1 and this is your beta 2, the class critical. And then the exponential of the coefficient here, it is very similar to the logistic regression where in the exponential of the coefficient or exponential of the beta is the odds ratio. But in this case, this is actually the hazard ratio since we performed a Cox proportional hazard model. And this is the standard error and this is the p-value. And again, we see additional result here, which is the 95% confidence interval. The ones here are actually exactly the same as this, so we don't bother with this anymore. Okay, so let's start with the class severe, wherein the hazard ratio is 1.79. Okay, so we have a null hypothesis here in which the hazard ratio is equal to 1. And the alternative hypothesis is that the hazard ratio is not equal to 1. Since the estimate of the hazard ratio for the class severe, the estimate for the hazard ratio, so I'm putting a caret sign here to denote that that is an estimate, is 1.797. And take a look at the p-value here. So the p-value is 0.235, which indicates that we're not going to reject the null hypothesis. Thus, our conclusion for the severe is that the hazard ratio is just equal to 1. And what you notice is that the 95% confidence interval here, which is 0.68 to 4.73, actually includes 1.0. That's why the null hypothesis was not rejected. And what does it imply? So it implies that the risk of dying among the severe COVID-19 patients is just equal to the risk of dying of those who have moderate COVID-19. So the moderate here, although we do not see here, it's understood that that is the reference. Because as we notice, the moderate was not
stated here because based on the levels of COVID, we had moderate, which is coded as 1, severe, which is coded as 2, and critical, which is coded as 3. Now, this is the reference here. That's why the model only has critical and severe. Meaning, whatever are the odds ratio here, it will always be compared to moderate. Okay, so since 1.79 here do not differ with the moderate, in other words, since the p-value is 0.235, then the risk of dying among the severe COVID patients is do not differ with the risk of dying among moderate COVID-19 patients. Now, let's proceed to the critical. Now, the critical also has a null and alternative hypothesis, which is the same as the one before, in which the hazard ratio is 1 and the hazard ratio is not equal to 1 for the alternative hypothesis. Now, for the hazard ratio, as we can see here, the hazard ratio is 8.0071. And take a look at the p-value of that. It's less than 0.05. Okay, it's very, very small. It's less than 0.001 actually. Okay, so it indicates that we're going to reject the null hypothesis and conclude in favor of the alternative hypothesis. And taking a look at the confidence interval for the critical COVID-19 patients, it's 3.2691 to 19.61. And that does not include 1.0. That's why the null hypothesis was rejected. So in other words, this implies that the risk of dying among the critical COVID-19 patients is 8.01 times confidence interval 3.26 to 19.61 as compared to the moderate COVID-19 patients. Again, our reference here is the moderate COVID-19 patients. So again, for the severe, the hazard ratio estimate was 1.7972. However, the p-value is 0.235. So the null hypothesis was not rejected. So in other words, the hazard ratio for the severe as compared to moderate is just equal to 1. Meaning whatever is the hazard or the risk of dying among the severe patients is the same as the moderate. That's why it's equal to 1 because the null hypothesis was not rejected. However, for the critical cases, the hazard ratio estimate for the critical when compared to moderate, that is 8.007. And the p-value is very small. That's why the null hypothesis was rejected. And our conclusion here is that the risk of dying among the critical COVID-19 patients is 8 times as compared to the moderate COVID-19 patients. So to summarize, out of 521, a total of 153 COVID-19 patients died in 2 months because we have here 60 days, so that is 2 months. And 153 is may actually be observed on this part. So we have 153, or basically that is the sum of 5, 23, and 125 here. So leading to a mortality rate of 29.3%. So that is 153 divided by 521, meaning for 153 patients died out of 521. The survival rates for moderate, severe, and critical COVID-19 patients are 94.4%, 88.0%, and 48.1%. Again, 94.4% is calculated as 89. And then we have 5 patients died out of 89, so that is 94.4%. Whereas the other one, we have 191 and 23 died. So the survival rate is 191 minus 23. So those are the number of patients who survived or did not die out of 191. So that's 88% for the severe. And for the critical, we have 241 patients, 125 died. So 241 minus 125 over 241, that is 48.1% survival. With a median survival of 15 days for critical COVID-19 patients. Again, that is That is found using this. So that's 0.5 probability, and that is 15 days here. And that actually may be calculated using the survfit function. So this is the 15-day median survival time. So further, critical COVID-19 patients are 8.01 times at risk to die as compared to moderate. So this 8.01 is calculated using the Cox regression model, which is this one, in which the reference again is the moderate COVID-19 patients. While the survival of severe COVID-19 patients do not differ since the p-value is 0.235 here for severe with the moderate COVID-19 patients. And relating our result with the Kaplan-Meier curve, it is quite obvious here that this critical COVID-19 patients really have low survival as compared to moderate and severe. That is why expectedly, actually, that the hazard ratio of this is much greater as compared to these two. So here we see that they almost have the same survival. That's why the p-value did not differ between moderate and severe. While this one is quite obvious that this has lower survival rate. Thus, we can see that the hazard ratio here is much greater. That's why the p-value here was less than 0.05, indicating again that the hazard ratio of those who are in critical COVID-19 is higher as compared to these two. So in other words, the lower survival, the higher the hazard ratio. So that is actually how we observe the Kaplan-Meier curve together with the Cox proportional hazard model. Okay, let's have the last example. We have the advanced lung cancer.R data, wherein this is about the 212 patients with advanced lung cancer from North Central Cancer Treatment Group. So performance scores rate how well the patient can perform usual daily activities is given as well. And the codes of each variable are as follows. So if we're going to open the file, the advanced lung cancer R data, we can see 6 columns, which are the ID, which is basically the patient ID, the time, which is the survival time in days, the status, whether 1, meaning the patient died, and 0 means that is a sensor data. The age in years, the sex, which is either male or female, the pH.ecog, that is the eco grade. Okay, so and the eco grade may be from 0 to 5, in which in this case, there's no patient which was grade 4 and 5. So that is only from grade 0 to grade 3. So 0 meaning the patient is fully active, 1 means the patient is restricted in physically strenuous activity but ambulatory, grade 2 means ambulatory and capable of all self-care but unable to carry out any work activities, and grade 3 meaning the patient is capable only of limited self-care. And then the last column, which is the weight loss, okay, in pounds in the last 6 months. So first thing that we may do is to get the descriptive statistics, like let's count how many patients died and censored. So we may calculate for that using the table function. So table parenthesis advanced lung cancer $ status. And we can see 62 patients died out of 212. Okay, and 150 are censored. And we may also compute for the mean age of the patients who died and did not die. So we may calculate that using the aggregate function, then age tilde, then status, then comma, then mean data equals advanced lung cancer, together with the SD as well, or the standard deviation. So there we can see that the mean age of the patients who died is 59.66, and the average age or the mean age of patients who did not die is 50.24, and then as well as their standard deviation. And then we may also create a table, or we may count the number of patients who died and censored according to gender. So that is table parenthesis advanced lung cancer $ status and advanced lung cancer $ sex. And there we see 37 males died and 100 males who are censored. Okay, then the rest are females. Then next, we may able also to count how many of them died and how many are censored according to different
eco grades, grade 0 to grade 3, using table, parenthesis, advanced lung cancer, $ph.ecog, and advanced lung cancer, $status. And lastly, we may calculate the mean weight loss in the last 6 months using the aggregate function, weight loss, tilde, and then status, and then comma mean, then the data as well as the standard deviation. And there we can see that the mean weight loss of those who died is 16.74 pounds, and the mean weight loss of those who are censored is 7.35 pounds. And then plus minus their standard deviation. And that's actually the one written on the next slide. So here we see the table that is simply generated using the aggregate functions and the table functions. And further, we may perform the Cox proportional hazard model or the Cox regression model, which will determine the factors in the death of advanced lung cancer patients. So in which the predictors are age, sex, the eco grade, and weight loss. So to do that, all we have to do is to type summary Cox pH, parenthesis serve, parenthesis time, comma status, then tilde, then the factors which are age, sex, pH, ecog, and weight loss. And then data, of course, which is the advanced lung cancer. And results show here that the hazard ratio, which again are the exponential of the coefficients here, and by the way, this is called as the adjusted odds ratio since this time we have many factors. So this is a multivariate Cox regression model. That's why this is AHR, or the adjusted hazards ratio, which are 1.03, 0.70, 8.87, 4.70, 1.41, and 1.00. And those are the one written here, as well as their confidence interval, okay, which are displayed here. So 1.01 to 1.06 for the age, 0.40 to 1.2 for the gender or sex, and so on. Okay. However, how do we know if which of these are the factors? Okay, all we have to do is to take a look at their p-values. If the p-value is greater than 0.05, then the hazard ratio is just equal to 1, meaning there's no evidence that the hazard ratio is not equal to 1. So meaning the hazard ratio is just as good as 1, meaning it's just the same as compared to, let's say, a certain reference. Now, if the p-value is less than 0.05, that indicates that the hazard ratio is not equal to 1, meaning 1 is more at risk as compared to other. So here we see that the p-values less than 0.05 are age, 2 levels of pH ecog, okay, or the eco grades, while on the other hand, sex and weight loss are not. So although in pH ecog, we can see that only 2 out of 3 are significant factors collectively. If at least one of them is a factor, then pH ecog is already a factor. So here we see again that age, pH ecog are the 2 factors affecting the death of advanced lung cancer patients. While on the other hand, sex and weight loss are not. And as we can see here, the confidence interval of those two includes 1.0. So remember that if the hazard ratio includes 1.0 in the confidence interval, this indicates that the p-value are greater than 0.05. Again, it's because the hazard ratio includes 1.0. However, on the other ones, we have age. The hazard ratio does not include 1, as well as this 2. The lowest is 2.06, and this one is 3.37. And the highest 10.7, 23.36. So in this case, the hazard ratio, the adjusted hazard ratio for age is 1.03. And note here that age is a numerical value. So how do we interpret the odds ratio when it is a numerical value? 1 unit increase of that will lead to an increase in the ratio by a factor of something like that, right? So meaning the age here, 1.03 indicates that an increase in age by 1 year, okay, an increase in age by 1 year increases the hazard ratio or probability of death by a factor of 1.03. Next, what do we mean by the eco grade of 2 and 3 here? So 4.7. So the eco grade 2 has an hazard ratio of 4.0770. So that indicates that the probability of death when patient has grade 2 ECOG is 4.70 times as compared to, there's no reference here, but we know that PCOG has 4 grade levels, right? Grade 3, grade 2, grade 1, grade 0. And grade 0 is not written here, so that is the reference. That's why here we see that that is a reference. So patients with grade 2 ECOG are 4.70 times more at risk to die as compared to grade 0 patients. And grade 3 ECOG patients, okay, those who had grade 3 in ECOG, this is grade 2, this is grade 3, is 8.87 times versus grade 0. So patients with grade 3 ECOG are 8.87 times likely to die as compared to grade 0. So these are the two interpretations. How about grade 1? So grade 1, since the p-value is 0.427, meaning the hazard ratio of that is as good as 1. So meaning the risk of dying for those who are grade 1 in ECOG is just the same or do not differ with grade 0. So that is what do we mean by that. So only grade 2 and grade 3 have higher risk of dying as compared to grade 0. Grade 1 does not differ with grade 0. And further, I want to introduce as well here what we call as the assumption in the proportional hazard, in which the null hypothesis is actually the hazards are proportional at any point in time. Okay, that's why a while ago I always tell that at any point in time, So the null hypothesis is that the hazards are proportional at any point in time, meaning the hazards do not change across time. It's constant, it's fixed at any point in time. Alternative hypothesis, the hazard changes at any point in time. Now, the Cox proportional hazard model, from the name itself, Cox proportional hazard regression model, it assumes that the hazards are proportion against time. So meaning that the hazard does not change across time. So meaning, in order for you to use this, be sure to satisfy the null hypothesis. In other words, if you perform this test, which is the proportional hazard assumption, be sure that the p-value is greater than 0.05. So in this case, the p-value is 0.43. Then we can say that this is the overall. So we can say that there's no sufficient evidence that the hazards are not proportion at any point in time. Thus, the proportional hazards assumption is met. So in medical journals, this is usually reported because this is the one that is usually observed by the journal referees. Okay, so whenever we see a survival analysis, there must be a proportional hazard assumption satisfaction in which the p-value again must be greater than 0.05 because that assures that the hazard is proportion against time. In other words, it's only the predictors who are affecting the death, and it's not about time. And that is what do we mean by the proportional hazard assumption. Okay, again, it's only the factors that are affecting the status or death, and it's not about time. Okay, so that's why at any point in time, meaning it's fixed. And lastly, why was this 431 and while this is 43? I just computed the p-value using this chi-square test statistic. So we may generate this using 1 minus p chi-square and then 5.9350 comma, and then we have 6. So you will generate 0.431 instead of 0.43. So to interpret this is just the summary of these results. So out of 212, a total of 62 patients died during the course of the study, leading to a mortality rate of 29.2%. So Cox regression showed that age and ECOG scores are predictors of the mortality of the advanced lung cancer patients, in which for every 1 year increase in age, The risk of dying at any point in time increases by a factor of 1.03. And then this is the confidence interval. Further, patients with grade 3 ECOG levels are 4.17 times, then this is the confidence interval, at risk of dying at any point in time as compared to grade 0 ECOG. So this is 4.17 versus the reference. While patients with grade 2 ECOG levels are 2.34 times, confidence interval 1.11 to 4.95 times at risk of dying at any point in time as compared to those with grade 0 ECOG levels. The survival of those with grade 1 ECOG did not differ, since this is 0.231, with those in grade 0 ECOG. So weight loss, which is 0.940, and sex, which is 0.212, are not evident as factors in the outcome. Then lastly, the Cox regression satisfies the proportional hazard assumption with p-value of 0.431. This ends this lecture about survival analysis. I hope you learned something in this video. Thank you.